Is the membrane potential. What is membrane potential? It's the potential difference across a membrane. This is a membrane and here is point A, here is point B. So potential difference from point A to point B, this the difference is my resting membrane potential, and it is when the membrane is resting. There is no ion and no cations moving in, moving out. This is how the membrane rests. Cool. Resting membrane potential, it is 70 millivolt, minus 70 millivolt. It's negative, so it means there is always some space for some positive anions and cations, positive charged particles. Cool. Why is this negative? A cell is just a bag of potassium in a sea of sodium. Always remember that. This is a golden rule, golden line. Cool, amazing line. So this is K, that is potassium, and this is low in environment. But again, cell is just a bag of potassium in a sea of sodium. So this is low in environment. Okay, so at rest the potassium moves out from the cell to extra membrane, and this is passive diffusion because cells are filled with K, so they want to go out for equilibrium, so they move out, they keep on moving out, they keep on moving out, they keep on moving out, and this creates a negative environment for the cell. That's why the overall is negative. Even at rest, the cell can give or take potassium. Yeah, I know. I mean, you should know that. I already know. So there are three factors that can change the resting membrane potential. First is potassium. That's the major contributor to resting membrane potential. That contributes around minus 86 millivolt. And this pump, sodium potassium pump, contributes about minus 4 millivolt. And positive sodium also helps very little. Okay, so you got it. By the way, normal serum potassium levels 3.5 to 5. Very important to remember this. Cool. Cell RMP. These are like, these are just normal levels of, by the way, like RMPs. So cardiac cells, they stay at 90. Skeleton is well 90. Neurons are 70. So these are like highly, even a little bit of positive charge can mess them up, because they are like really negatively charged. Okay, if they are really negatively charged, they are like, okay, we'll talk about it. Wait. So cardiology. So cardiac cells stay at negative 90. Skeleton cells, skeleton muscles, they stay at minus 90. Neurons minus 70. Pacemaker cells, they don't really have any fixed resting membrane potential. They have a range, and this range is minus 60 to minus 40, and this range is unstable RMP, and we call it restless potential. Why is okay, I was thinking about to name why it's called restless. It's just restless because it keeps moving up like this. There's no fixed resting membrane potential, RMP. For example, cardiac cells are like this. It sits at 90, but these pacemaker cells, for example, SA node, Kagel cells, pre-Botzinger complex, these cells are they stay at this range. So that's why it's restless. It keeps changing. Cool. We know these are like restless cells. Okay, what about hyperkalemia? What is hyperkalemia? Hyper means hyper, kalemia means potassium, K, and emia means in the blood. Okay, so extracellular potassium is increased. If the extracellular potassium is increased, cells, and outside is a lot of K, positive, what will happen? This will create a deficit inside the cell. Cool. Again, a lot of positive outside, seen in rhabdomyolysis. Diffusion is stopped because of this disease, and the potential is depolarized as K are not leaving the cell, as extracellular environment has a lot of potassium outside. Why would this K, which is little bit inside, there are 3K inside and there are 15K outside. Just imagine there are 15K outside. What will happen? Of course, there will be movement of from outside to inside, but not the movement from inside to outside. Cool, now you get it. So the potential is depolarized because cells, these plus is not leaving the cell. And we need this cells to get rid of K so that the RMP can become negatively charged. So this RMP, what happens is that eventually after some time in this disease, this K is not leaving the cell and this RMP becomes really positive, So this membrane is really excitable now, But what happens in hypokalemia? Outside is very less, inside is a lot of K. What will happen? They will jump outside to achieve equilibrium. Okay, and once they jump, the cell becomes highly negative. Okay, so extracellular is very less. K rushes outside the cell to extracellular. Cell becomes more negatively charged. It's less excitable because, okay, so just imagine your RMP is here, right? It's minus 90. But during hypokalemic stage, what happens is that your RMP dips and it dips to maybe 130. So just imagine any threshold voltage is here. Maybe 20 degree, 20 millivolt is your positive 20 millivolt is your threshold electro condition for any sort of action. So imagine your cell is even in 130. More number of positively charged ions are needed for your cell to touch that plus 20, to touch this plus 20. Now if your cell was at minus 90, less number of cells would need it to touch plus 20. But now after hypokalemic stage, your cell goes at 130, minus 130. So your cell needs more ions. So it's very much less excitable now because your cell is now resting at 130 where it should rest at minus 90. Cool, you understand it now. So that's why we say it's less excitable because you need a lot of anions now. But here in rhabdomyolysis, you don't need a lot of ions because your cell, which was at 90 minus 90, now the new RMP, because of the hyperkalemia, the new RMP is like maybe minus 45. So even a little anion can, excite this cell. So that's why the cells are more excitable now. Cool, now we understand this. Okay, less excitability is called hyperpolarization. Polarization means it's either a lot of plus or it's a lot of negative. So it's polar, so it's hyperpolar. It means it's a lot of negative. What about this? It's dipolar. It means in cell we say like polar is minus. So if I say dipolar, it means plus. Cool. Hyperpolarization. This negative environment will try to attract positive, of course, because cell is now sitting as minus 30. There is a deficit. There is a lot of space for charges to come inside. So this attraction of charge from ECF, extracellular fluid, to intracellular fluid is called electric gradient. So electric gradient and this concentration gradient, right? So what happens? Okay, let's see. When this is, both equal, this electric gradient and concentration gradient of charges, we achieve equilibrium potential. What is equilibrium potential? We call this equilibrium potential because there is no ion movement, because outside and inside both have achieved equilibrium, nirvana. So there is no current flow. Cool. We call this isoelectrical potential. There is no transfer of ions. So concentration gradient of ion equals to electric gradient of the ion. So we have achieved equilibrium. So no traveling of ions, man. Okay, so ion moves with concentration gradient from high to low because they want to achieve equilibrium. What about electric gradient? Electric potential is calculated with respect to the inside of the cell. So we take inside of the cell as point A and the outside of the cell as point B. And we always calculate the electric charge of the cell in respect to point B. We take point B as 0. We take outside as 0. So to bring anything from outside to inside, we calculate how much work is done. So we take outside as 0 and we take inside as some whatever the value is. So outside is considered 0 millivolt. So that's how we calculate this equilibrium potential. Cool. Tak. Okay. Let's talk about other minerals, not minerals, ions. So there is positive, chlorine, calcium, sodium, potassium. Cool. Now you know. So what happens is that imagine if the concentration of sodium is high outside, what will happen? It will jump inside because cells are not high in sodium. So equilibrium of sodium ENA is plus 60 because it's going in, and it's plus. So we denote as plus 60 millivolt. What about K plus? They are high in cellular, and extracellular they are low, so they want to jump out, so it's negative. If they want to jump out, it's negative. If they want to come in, it's positive. Because if we make some money in real life, we add this money to the bank, so it's positive. And if we lose some money, it's negative. Cool. You understand this now, right? So the charge is positive. Cool. Doesn't matter. The value is, and we lose it, it's minus negative. Again, chlorine, we take this as 0, and we take chlorine from outside to inside because chlorine is high outside and less inside, because chlorine is really negative, and then our cell is TOJA 2 negative as well because RMP is negative on default, so it like deflects. So this comes inside, and equilibrium chlorine is minus 90, same as RMP of neurons. What about calcium? Highly volatile, so it's like a trigger. If you get a lot of calcium inside your cell, a lot of things can go wrong or go good because it's a trigger ion. It can trigger a lot of processes. So equilibrium of calcium is plus 30 because we are taking in. This is minus 70 because we are taking this inside. Cool. Okay. Why chlorine is less in the cell? Because cell is already negatively charged. Chlorine repels. Cool. But calcium is positively charged. Then why calcium is less in cell? Because even small calcium can trigger big pathways. To keep cell stable, cell keeps calcium out, as calcium is plus 130 millivolt. It's a lot. It can change the whole potential difference of the cell. So that's why we don't want a lot of calcium in our cell. What is Nernst equation? We can calculate we can calculate this equilibrium ion by using Nernst equation. Plus minus 61 log of concentration outside, concentration inside, or this is for one ion. Or we can use, in real life, multiple ion play a big role, yes, of course. Or we can use this thing called Goldman's equation. He even considers permeability ion, because Goldman's equation considers permeability of ion, like how permeable an ion, like some ion is, and they take this formula as well. So Goldman is better than Nernst. Cool. It's just history. That's it. What about driving force? What is driving force? Driving force is resting membrane potential minus the equilibrium potential of it. For example, driving force. What what is the driving force of sodium? Resting moment potential of the cell is minus 70. Equilibrium potential of sodium is plus 60. So it happens minus 130. So it means that there is a huge driving force for potassium inwards inside the cell. Okay, cool. From ECF to ICF, extra to intra. So whenever possible, sodium tries to run inside because the driving force of sodium is 130 millivolt. So minus 130 means there is a huge space for ions to rush inside, because negative is not really negative charge, it's the absence of charge. That's why it's negative. Cool. What's about chlorine? So RMP minus equilibrium chlorine. We know chlorine is same as resting membrane potential of electron. So minus 70 minus get plus, so it's 0. It's neutral. So if the driving force was positive, the charge leaves the cell. If it was positive, there is no space because it's already positive. So already charges are inside, so they want to go out. So you understand this concept of driving force. Protein, DNA, RNA are not diffusible, of course, because they cannot go out. If they go out, what is cell? Nothing. So DNA, RNA can never go out, and these are negatively charged ions. They hinder with the electronegativity of the cell, of course. So we call this Gibbs-Donan effect, that these protein, DNA, RNA can hinder with the electronegativity of the cell. We call this Gibbs-Donan effect, and they change RMP, the resting membrane potential. What about colloid oncotic pressures? So colloid oncotic pressure, I'm talking about blood capillaries. I'm talking about plasma proteins like albumin and globin. And these make pressure, like, the concentration gradient. And the pressure is pi C. And this is the reason fluid is reabsorbed from the interstitium. This is actually one of the mechanisms how you don't develop edema. And they attract water inside. And if it's messed up, you get interstitial fluid, and then it leads to edema. And usually this oncotic pressure is more than what your capillaries need. For example, your capillary may need just 21 millimeter of Hg, but usually what oncotic pressure is 28 millimeter of Hg, and this 7 millimeter of Hg is like a security. It's like the safety net. It's like a little bit more, so that some of the interstitial fluid can go back inside the capillary. So that's the concept. Okay, what about cellular fluid? I think let's study cellular fluid in the next video. I think that'll be a good plan.